Okay, so I will wait a little to start before, but maybe we can discuss about some few preliminary information, like like the lab today. So I hope you have seen the message I left in Canvas. So all of the groups will participate at the same time to the lab. I divided into room. The official room is D381, but the D386, which is the room aside, is usually empty, and we will take over that. So you all of you can do the lab at the same time. The equipment for the antibacterial and cleaning papers and so on, and the mask is everything, should be everything in the lab. So whenever you arrive there, even if you arrive before me, then you're free to take them. And yeah, I think you know now how it works, the lab. Today we don't use any equipment. We are going to use mainly your laptop. So I hope that every one of you brought your own laptop. And yeah, so then whoever I've already started to work with Isieda, then is already have done some, is in advantage, so he has to do less in the lab. Who didn't start is okay. You haven't today 3-4 hours to finish it. So as you will see, the lab also with the increase of a little, there is a curve, there is a parabolic curve. So you will feel that now the lab effort will start to increase a little. So it will require maybe a little more effort from you, little by little, until maybe operational amplifier. Then as soon as we finish that, the effort from your side will decrease, because it should become more easier. Should become easier. And yeah, so this is the second lab, and next time we will study in the lab the software, the LT-Spice. Today we study the other software, which is called Isieda. And then I think you got almost of the knowledge about all the software you have to use in this course, which is again Isieda, LT-Spice, MATLAB, and Tinkercad. Yeah. Is anyone has any question before to start on about the oblique? I'm not sure. It doesn't seems. Okay. So I already set my presentation in the filter design. Today we study, or at least review a little about filter design. Again, it will be part of review and part new, because I will give you my perspective of filters. Today, mainly, we are not designing filters. We are trying to give an physical interpretation about filters. So try to understand why they behave like that, and why they operate in such a way. So we are going to investigate better and try to understand how filters work, although you already know, hopefully. But yeah, we're going to look into the details of it. Yeah, so let's wait maybe another minute and then we start. Okay, now my clock is 15, so we start. Again, there are many things to do. I'll try to go slow also because I'm sleepy. But let's start with the filter design. Okay, so I will maybe try to do part of it on the slide and part of it on the tablet to show some calculation, but you know my style, so if I can, I will try to show the calculation, but there is some theory here, so I will present it on the slide. Okay, we are going to start with the passive filters, and then we are going maybe to design one to filters like high pass filter and low pass filter. Okay, so let's start from very simple things. So what is a filter? Well, the filter, there are many type of filter in your daily life. So not only electrical filters, but also mechanical filters and also other filter that you actually use to see every day, but maybe you don't call them filter. This is an example on your right side of a type of filter where you know you have to extract the juice from an orange, and this net, let me change the pointer, this net here that you can see in this part of this object is the filter. So when you press the orange toward this object, the juice will come out, the juice will pass through the hole, but the holes will retains the pulp. So the orange pulp will not go through this hole and will get stuck here. So this is kind of like a filter. So it's letting pass the juice, but it's stopping the pulp, which remain all over the filter. So in a few words, a filter, so in order that everyone can have an idea about the general definition, is something that stop certain things, but let pass other things. Um, in electronic, the filter has the same purpose, but of course in terms of electrical signals. So the filter in electronic let pass certain type of signal within certain range of frequency, and the other signal which are not inside of this range of frequency are stopped at the input of the filter. So all the signals which are within the range of frequency and they are applied at the input of the filter, they can pass through the filter if they are in this range of frequency, which we will see later is called pass band of the filter. Instead, if they are not inside of this range of frequency, then the filter will stop the signal at the input, and the input signal cannot pass through the filter. So this is a simple way to stop or to remove some signals that we don't want that go through our system, right? For example, the noise. Noise is a signal that we don't want in our circuit. So sometimes placing filters in our system allow the system to stop the noise and don't let the noise reach the other part of the acquisition system. The filter in electronic circuit is usually analyzed by using input signal which are sinusoidals. So usually you can describe the behavior of a filter if you apply a sinusoidal signal with a certain frequency and then you measure the output, right? We will see that there are particular parameters of the output that are interesting for us. For example, the amplitude and the phase shift of the output signal, of the output of a filter. We will see later on then these concepts, but for the moment, I would like to summarize the fact that there are 4 types of filters. Maybe you have seen 3 at the moment in LLC. The first is low pass filter. Then we have an high pass filter. We have a pass band filter, and we have a Here I wrote it wrong, but it's a notch filter with N-O-T-C-H, which is also called a stop band filter. So here I wrote it badly, I have to fix it here. So low pass filter let pass to the output all the signal with low frequency. So there will be a threshold, which we will call cutoff frequency, and all the signals with the frequency lower than the cutoff frequency will pass through the filter. Instead, the high pass filter is a device which let pass to the output only the signals with very high frequency. So all the signal which have frequency greater than the cutoff frequency, then will go to the output of this. Passband filter is a filter which let pass the output signal to the output signal only the input signal that have frequency between two value. Okay, so only signal that are in a certain frequency range between FC1 and FC2. We are going to calculate this parameter later on, but this is just definition. So instead, the stop band filter or the notch filter let pass practically all signals except those ones that are inside of the range VC1 and VC2. Okay, so it let pass all the signal with frequency lower than FC1. It let pass all the signal with frequency FC2, but not those one between FC2 and FC1, where FC2 is greater than FC1. So, but again, I told you that in the previous class that when we say low or high, we always have to specify what does it mean. As engineer, we always have to say low respect what and high respect what. So again, this is why before I specified, when I said low frequency, I specified the fact that the frequency has to be smaller than FC, the cutoff frequency. And here I specify that the frequency of the high pass filter, the frequency of the input signal should be higher than the cutoff frequency of the high pass filter. So it's always important to specify what does it mean high and low here. What are FC1 and FC2? So we're going to look soon what are these two parameters. Let me see here. Okay, so for the ideal low pass filter, so I'm talking about ideal. Okay, this is very important. We start from the ideal situation. As I said before, the signal with a frequency smaller than the cutoff frequency will pass through the filter and reach the output. If the input signal has a frequency larger than the cutoff frequency, then it cannot reach the output. So from a mathematical point of view, you can describe the filter in this way. So if the F, the frequency of the input signal is smaller or equal to the cutoff frequency, then the output is equal to the input because the input passed through the filter and reached the output, right? So when the frequency is smaller than the cutoff frequency, the input passed through the filter and the output is equal to the input. If the frequency is higher than the cutoff frequency, then what happens is that the input cannot pass. So if the input cannot pass through the filter, then there is no output, which means that the output is zero. Yeah, how to represent in a simple way this mathematical condition. So again, as engineer, if we have a plot or a graphical representation of the mathematical formulas is always much better and very useful for us. As engineer, we need to know the math because sometimes we need to solve new problems, and to solve them we need to know very well the math behind all the electronics. But very often graphical representation for design are much easy to use and faster to achieve the purpose, which means to realize the device. Okay, so let's have a look how to create a graphical representation for this condition here that you wrote. Again, these are the conditions for an ideal low-pass filter. So in particular, as I said before, when we talk about filters, what we are actually interested in are two parameters. The first one is the amplitude, and the second is the phase or the phase shift. And I will explain soon why. First of all, as you can see from the definition here, if the frequency is smaller than the cutoff frequency, then the output reach and then the input reach the output of the filter. This means that the output signal is identical or equal to the input signal, which means that the amplitude of the output is equal to the amplitude of the input. Okay. Instead, if the frequency is larger than the cutoff frequency, the output is zero. So it means that the amplitude of the output signal is zero. So it's very simple to understand the behavior of a filter in terms of amplitude, because the amplitude of the signal will be zero for f greater than fc, and the amplitude will be equal to the amplitude of the input when f is smaller than fc. I hope that you are understanding this equation, because again, later on I will use a little more complicated equation and more compact to represent the filter in a compact way. So it's very important that you follow this part. Okay, but let's say, how do we describe usually the amplitude of signals? Okay, let's say we said before that when we study a filter, we usually do it with sinusoidal signals. So the input signal of the filter is described here and is written in terms of sine wave. We have the amplitude here, then we have the frequency, angular frequency, time, and the phase, the initial phase. Phi in here is, input phase. And this is A in. A in is practically the amplitude we are looking for. So it's the amplitude of the input signal. Same for the output. Again, if a circuit has an input signal of sinusoidal signal, then of course all the signal in the circuit must be sinusoidal. That's why I can write V out in sinusoidal form. Okay, this is very important. One thing that I didn't mention, and maybe it's very important, and probably someone maybe is thinking about it now, is the fact that I always say that electronic circuit to work need power supply. So, and I didn't talk about power supply in filters. Well, in the case of filter, in the case of passive filter, as what we are studying here, this device does not need power supply because it's passive. And you have seen already when I presented yesterday the sensors, that there are two types of sensor, the active sensor and the passive sensors. The passive, in general, passive devices do not require power supply. They still require an electrical signal, of course, which in this case come from the inputs of the filter, but does not require a power supply to work. Because these circuits are just made of passive elements like resistance, inductance, and capacitance. And a resistor, in order to have a certain resistance, does not need a power supply, neither capacitance, neither the inductance. So whenever you have a circuit which does not generate any signal, so it's not active, then you have that you don't need a power supply. So for this reason here, we have just the input signal, and then we have the output signal, again, both sinusoidal. And the output signal, of course, will have most probably different amplitude than the input, so I call it A out. And most probably will have different phase than the input, so I call it phi out. Okay, and so what we are interested in actually is A in and A out, which are the amplitude of the input and the output. In electronic, we used to write the input the signal amplitude by using this symbol here, which is the absolute value. And this will represent also the magnitude. Because again, I didn't go in detail, but a sinusoidal signal can be written in phasor way, and phasor are expressed in terms of magnitude and phase, which means in terms of this term here and this term here, but here in between there is a complex exponential. So in our case, we are interested on this part, which is the magnitude of that phasor. But if you want a physical representation or physical meaning of this, the magnitude of the phasor, then it's just the amplitude of the sinusoidal signal. The same for the output. So this is the symbol we will use for represent the amplitude of a signal, of the output signal. So we are interested, and we sometimes we will call it magnitudes. Okay, if I say magnitude or amplitude will be the same. So the input magnitude, the input signal magnitude is this one, and the output signal magnitude is this one here. So if I take the previous condition, which is this one here, and I rewrite it in terms of magnitude again, I can say that if the frequency is smaller than Fc, which is the cutoff frequency, then the magnitude of the output is equal to the magnitude of the input, which means that the amplitude of the output is equal to the amplitude of the input. The frequency, if the frequency of the input signal is greater than the cutoff frequency, then the amplitude of the output is equal to 0. Therefore, if I want to represent this one very easily on a plot, I can just draw two axes, the frequency axis here, because the variable is f, and also a y-axis, which is the amplitude of the output, which is what I want to find, right? So if the frequency, so in this range here, is smaller than fc, then we have that the output amplitude is equal to the input. So here the curve is like this. So it's constant to the input amplitude. Instead, if the f is greater than fc, so in this part here, then the output amplitude is 0. So this is a simple representation of an ideal low-pass filter. Now, from here, unfortunately, yesterday I didn't have my notes with me, my charger of the laptop, which I forgot in my office, so I had to write with my pad. So maybe you won't understand here, I will try to discuss it better. But again, if I remember now correctly from yesterday, you wanted to have the slide in Canvas, so maybe I can upload this one in Canvas. Let me upload it now, so if you want, you can follow also there. So here we go, save. Okay, I'm going to save now the PPT in Canvas because it was updated, so you may have the older version, which means the part of the filter. Okay, I think now it should be in Canvas, so whoever wants can go to the filler, microelectronic, electronic circuit design, and then in the Forelesning 2001-2020, you can find the presentation. Okay, then I will continue. Let's see. Yeah, although this one is a nice representation for a filter, this makes us think that the behavior of the filter depend on the input. Because of course here the curve, that this red curve that represents the behavior of the filter depend on the value of the input. Of course, the behavior of the filter does not depend on the input. The filter is a low-pass filter regardless what is the value of the input. The only thing that change is just this value here. It can be 3 volt, it can be 5 volt, depend on the input signal, but it's still a low-pass filter. And what we want actually highlight or understand from this plot is just that is a low-pass filter. So what we want is a representation which just show show to us the behavior of the filter. So it's a general representation which is independent from the input amplitude. So what engineers do usually, this is often one method that is you will see in many, hopefully in many courses because it's often utilized, is a normalization. So it's an operation which normalize the amplitudes, which means that you practically take this plot and you divide this plot for the input signal amplitude. If you take this plot and you divide for the input signal amplitude, you obtain that the y-axis is equal to the output amplitude divided by the input amplitude. But finally, we have a curve which value does not depend on the input, let's say, is normalized between 0 and 1. So this one, it represents better a filter, a general filter. So this curve, the height of this curve does not depend on the input amplitude, right? And from here, we can just extract the behavior of the filter. So normalization, which is the operation of transforming this plot dependent on the input in a plot which is not dependent on the input, transform the curve from 0 to Vin to 0 to 1. It's a very common method. So then this parameter here, which is actually the y-axis meaning here, it has a very important purpose and meaning. It's usually called frequency response of the circuit. And of course, is a function of the frequency. Here I wrote omega, but here I put f. Remember that when I use f or when I use omega is the same things because they are proportional and they are proportional for a 2 pi constant. So sometimes you will listen that I say frequency, I write omega, or sometimes you will listen that I say frequency, I write f, is the same. It's just a proportional constant that is different. Okay, so this ratio here is a function of the frequency, as you can see, changing frequency. So it's a function of frequency. But we will not indicate it with f omega, we will indicate it with h omega. And because this ratio is a ratio between magnitude, this one we also put the magnitude symbol here. Okay, so if you repeat the same procedure that we've done for the low pass filter, then you will get the similar plot for high pass filter, band pass filter, and notch filter. For a high pass filter, you have that the magnitude is equal 1 only if f is greater than fc here, and the magnitude of the frequency response is equal 0 if f is smaller than okay, here I should have wrote fc, another error. Okay, so in the plot I wrote omega c, sometimes fc, to show you again that it's the same if I use f for omega. Of course, if you use omega here, maybe it's more coherent to write omega c1 and omega c2. Probably I was sleeping a little in that night, but it's always better to be coherent, right? So if you write omega here, write omega c, omega, and here write omega c1 and omega c2. But again, in the end, the important you understand that writing omega and f, they are kind of like the same thing. Yes, so here there should be an FC, okay? There is an error here. And yes, so what does it mean here for the high pass filter? For example, it means that saying that the frequency response magnitude is equal 1, it means that is in this region, the output amplitude is equal to the the input amplitude, and here is 0. Saying that here the frequency response magnitude is equal 1 in this range, so between these two frequency here, it means that in this range of frequency here, the output amplitude is equal to the input amplitude, while here is 0, the output amplitude. And the same for the notch filter. Okay, so maybe this part I can do it on the pad, a few calculation, just to show how they are real filter. So we are going to study a little the real filter, because this again, are the plot of filters, but they are ideal. Again, I just taking in consideration here the low pass filter. This means that after FC or omega C, which is the cutoff frequency, after that, no output signal. There is no output signal from the filter. So all the input signal with the frequency greater than the cutoff frequency, they cannot reach the output. So their amplitude will be 0. Okay, so let's do some calculation. Let's see. If you have any question, just feel free to ask. So let me see. So here at page, here right, filter. Okay, and then I share the screen. So I hope that you can see the screen. And let's start with real filter. So as I did before, I start from the low pass filter. All the procedure can be repeated with high pass filter. Maybe I will do also that. So it's very easy. And let's see. Okay, so the simple way to realize a low pass filter is just by using an RC circuit. So here in the left we have the input, here in the left we have the output. Okay, so we want to understand, we want to extract the real plot of low pass filter. Again, so this means that we want to find the plot like this, omega, but for a real filter. So for this filter here. So in other words, if you don't remember that this is a low pass filter, or if the circuit was a little more complicated, I will show you the method that I usually use for extracting this plot here. Okay, this is a general method and you can use it regardless. It is a way to have an idea about the plot, a first idea about the plot, and it gives you a method for estimate this. Let me see. Yeah. So let's start. First of all, we are going to calculate the output, because remember that what we want to find is this magnitude of H omega, which is equal V out, let's say omega divided by V in omega. So V in usually is a signal, and we said before, is a sinusoidal signal that you have your signal generator, you know how much it is. So this is something that usually is known, okay? We know that. What we don't know, of course, is the output. So remember that when you do a circuit, always start from the output. Don't start to write a bunch of formulas without no reason. So always start from what you need to find. So the output of this circuit derived from the knowledge of electricity Kretzer. So you know that when you have a sinusoidal signal, we have to use the impedances. I will try to do all the step anyway because we are sleeping, so I will make it all the simplification possible because I'm sleeping at least, so I do it very simple. Here we are. So as you can see, I substitute the capacitance with the impedance, and now I can find the formulas for the output by using the voltage divider formulas, but this time for the impedances. So this means that the output is equal V in multiplied zeta C divided by zeta C plus R. Now, what is zeta C? I hope that everyone remember, and we also see last time. Zeta C is equal 1 over J omega C, 1 over J omega C plus R. And now, again, if you do take everything in common, then you get, let's do all this stuff, okay. 1 over J omega C divided by, here taking common, J omega C, 1 plus J omega C R equal This one go away with this, and then we get finally 1 over plus G omega CR. Okay, so this is the formulas for the output, very fast. Of course, since I'm sleeping, I forget one term. So one here and one here. And yeah, so this is the formulas for the out. So let's circle it. Big achievement. Okay, and but what we are actually interested in is not V out in this form here, but is the magnitude of V out, right? So is the absolute value of V out. So we need to calculate the absolute value of V out because this one is what represents the magnitude. So then we apply the absolute value. I hope you remember how to calculate the absolute value of complex number. So here write V in. Okay, let me write some number, otherwise we don't know, maybe. Yeah, like this. And then we're going to calculate the absolute value. So in the top, the denominator remain 1, and the absolute value of a generic complex number is equal real part square plus imaginary part square, everything under the square root. And here is V in. Oh, finally, from this equation, we can calculate the absolute value of H, because if we divide all of this equation here with V in, we get V out divided by V in, which is equal what we want to find, equal to 1 over square root of 1 plus omega square, C square, and R square. So this is finally is the formulas that we want to find. I derived from the previous one by dividing everything for V in, for the absolute value of V in. So how do we plot this? Okay, the trick is this one. I will show you now a method to estimate more or less what will be the plot. Of course, to have a better idea, you need to have, you need to know, you need to evaluate this function here for all the value of omega. I will show you then with the Laplace transform, which will be much more easier, much easier. And if you know the Laplace transform, you can draw the plot of a frequency response maybe in 5 seconds. But unfortunately, now we are here stuck with this complex number. So yeah, but let's anyway do this. So the trick is this one. When you have any frequency response in front of you, what you have to do is the same things that I hope you have done, or hope that your teacher in mathematics have teach you, which is called analysis of function. And in particular, analyze the behavior of the function at the extreme of the domain. What does it mean? In our case, the domain of our function is 0 to plus infinity, which is practically the range of frequency. This defines the domain. And so we have to go to evaluate our function at the extreme, so at 0, at infinity. So what we are going to do is calculate the limit for omega that go to plus infinity. But what does it mean actually? What are we doing by doing this? In other words, what we're doing is trying to understand how the filter behave at very high frequency and at very low frequency, okay? So we have to know very well what the math means. So yes, the limit here symbol is very fancy and very nice, but what actually we are looking for is just to understand the behavior of the filter at high frequency. This is what it means, the limit, okay? Always try to give a physical meaning of the mathematics you use. So the limit of omega that go to plus infinity of our function. So I will write it here. So we are going to try to understand how the filter in terms of amplitude behave at high frequency. This. So now I think this is pretty easy for you and pretty trivial. If omega go to infinity, the denominator of this formula go to 0. So the denominator go to infinity and the ratio go to 0. So the result is 0. So this means that the plot of our frequency response, right? We expect that for very high frequency will drop to 0. Okay, we don't know how, we don't know when we'll reach 0, but I mean, we know that we'll reach 0 at infinity, so I cannot let this curve touch the x-axis because it will never reach it, right? Only at infinity, so I can draw it like this. But we know that it's approaching 0 for high frequency. Then we repeat the same things for omega that go to 0. So we want to study the filter behavior for low frequency. And here write h omega equal to the limit of omega that go to plus infinity of our function. Yes, so again, here is pretty trivial. Another error here, 0. It's pretty trivial. So if omega go to 0, this term here go to 0. So 1 plus 0 is 0. 1 plus 0 is 1. Square root of 1 is 1. So 1 divided by 1 is 1. So this one go to 1. Okay, so then we know that for very low frequency, like this, we know that the function will practically go around 1. And here we know that this one go to 0 here. So let me write low frequency, and this is the behavior of a high frequency. Now, to know what are the point in between, as I said before, there is no easy mathematical way or approximated way to do that. We can do an extrapolation of the data, which means that as engineer, what we can do, we can guess what will happen in between, although it is a guess, it has to be proved. But at least our first guess could be that in between does like this, right? So by studying the filter behavior at the stream, so at low frequency and very high frequency, you can have an idea more or less which kind of filter it is, because even though we don't draw this part, we know that at a high frequency 0 and at low frequency is 1. So this one look like very much the behavior of an ideal low pass filter, right? Because the low pass filter is 1 for low frequency and is 0 for high frequency. So, and then we can imagine that is like this. This is our guess. It has to be proved. But again, if you solve this equation here, if you evaluate this equation for all the omega, you will find that. But if you have any other equation, you can guess this one here, but then you have to prove it in some way. Okay, so then we have finally the frequency response for the real, I draw it like this maybe, for an RC low pass filter. Okay, here is 1 and here is 0. Again, why I say this is a low pass filter, because the high frequency are stopped. The amplitude of input signal at high frequency are 0. So this is why this one is a low pass filter. Let's compare this plot with the ideal one, right? So I draw here the ideal, then and then. Okay, and you know that the ideal has a cutoff frequency, which is called FC. Now the point is this: how do I decide where is the cutoff frequency in the real plot, right? So this is the real and this is the ideal. So how do I know where is the cutoff frequency in the real plot? So where is the cutoff frequency here? Is not so straightforward as in the ideal plot. So the engineer has defined that the cutoff frequency is the frequency at which the power of the output signal become, let me write it here, the power of the output signal become half of the maximum power, P out max divided by 2. Yeah. So this is the definition of cutoff frequency. I think probably you're gonna give you already the final definition, but I think it's good that you know how to from actually you come from. So the definition that the engineer gives is that at the cutoff frequency, the power of the output become half of the maximum power that the output can achieve. Now, if you remember that the output is a sinusoidal signal, you remember that the power for a sinusoidal signal is equal the maximum voltage multiplied for the maximum current divided by 2. This is the power formulas for a sinusoidal signal. And if you, for example, have that the voltage signal is across a resistor, then you know that this one can be written like this. So R is practically an imaginary resistor that I connect that I think is practically at the output of the filter, okay? So this is the power dissipated by the resistor R if it was connected imaginarily with the filter, at the output of the filter. And yes, so what about the power at the output of our filter? So of course, what we have to do is calculating the power here at omega c. So the power at omega c, how to calculate the power at omega c? The power at omega c, based on this definition here, is V max, V out max squared divided by 2R. R is an imaginary resistance. It's not the resistance in the filter, okay? It's important to know this. This is not the resistance in the filter. Let me call it R star, so you don't get confusing, R star. And so this is the power of the output at omega c. Remember that V out max, we usually indicate it like this, right? V out max is the peak voltage or maximum amplitude. So I rewrite these formulas like this. And then we say that the power at omega c, it has to be equal to half of the maximum power at the output. So half of the maximum power. And what is the maximum power? The maximum power is equal to V out max square divided by 2R star. So from this equation, I take this one here. This is V out at omega c, of course. And then I take this part here, right? I take these two parts and I write in only one equation. So V out omega c square divided by 2R star equal to 1 divided by 2 V out max square divided by 2R star. Now here we can do some simplification. This one go away with this one go away with this. And remember that how much is V out maximum? So what is the value of V out maximum, the magnitude? If you remember before, V out maximum is equal practically V in, because again, we know that the output is maximum at low frequency for this low pass filter, and at low frequency, the output amplitude is equal to the input amplitude. So V out max is nothing else than V in amplitude, okay? So this equation can be written as V out omega c equal to 1 divided by 2 V in square divided by, I think like this should be okay. So like this. Okay, so then we do the square root everything, and finally we get V out omega c equal to V in divided by square root of 2. And we can finally find the value that we were searching, which is the frequency response at the cutoff frequency is equal to V out divided by V in. Of course, everything evaluated at the cutoff frequency. This is equal to 1 over square root of 2. So remember that if I have this plot here that I see before, let's try to give a meaning to this equation. I will finish this part, then we take a break. So what does it mean, this equation I just wrote? It means that the frequency response at omega c will be equal to 1 divided by square root of 2, which means I have to check here where is 1 square root of 2 divided by square root of 2, and then the frequency of this point will be the cutoff frequency. Okay, this is how the cutoff frequency is defined. I don't know if anyone derived to you, but this is how it is. Don't take the definition of cutoff frequency as it is. You always need to know where they come from. However, again, let's try to reconnect with maybe what Jürgen told you before, is that usually this kind of like a plot are plot in terms of dB. So if you remember maybe a value in dB, let's say a voltage in dB, because we work usually with voltage, a voltage in dB is expressed as 20 logarithm of 10 of the voltage signal. Right here. So in our case, we don't have a voltage, but we have the absolute value of H. So the absolute value of H at omega Okay, let's do like this. So then let's transform this plot here in dB, like this. Omega, and now here is this one in dB. So we know that here it should be 1, right, in normal value. But how much is in dB 1? So we have to do 20 logarithm in base 10 of 1. How much is logarithm of 1? Logarithm of 1 is 0. 0 times 20 is 0. So this is 0 dB. And how much is here? Well, here in theory, if you base it on what we did before, it should be 0. So we have to transform 0 in dB. How much is 0 in dB? Logarithm in base 10 of 0 is minus infinity. And minus infinity times 20 is minus infinity. So actually, when you transform this plot in dB, so when you transform this plot in dB, you get that the plot will become something like this. So it does not stop here because it goes to minus infinity, okay? So this is the plot of a low pass filter in dB. And then this one, as I said before, is going to minus infinity. Now, what is the value where we have the cutoff frequency in dB? Again, we don't have to base our answer on our memory. We always have to be able to derive our answer. So what we have to do is nothing else than the frequency response at the cutoff frequency is equal, in dB, of course, is equal to 20 logarithm of 10 of the frequency response at omega c. We know how much is this value because we calculated before, is 1 over square root of 2. So 20 logarithm of 10, 1 divided by square root of 2. This is equal 20 logarithm of 10. Let's hope that you remember the logarithm properties. 20 logarithm of 10, square root of 2. And this one is equal to 0 because the logarithm of 1 is 0. And then we remain with 20 logarithm of 10. I try to do all the steps so you remember these things. Little review of mathematics. I take the exponent and bring it outside. So this one becomes minus 10 logarithm of 10 of 2. And then logarithm of 2 is something, logarithm base 10 of 2 is something that usually is known to engineers because we always work with logarithm of 10, logarithm of 3. This is some numbers that come out often. So this value is approximately 0.3. So minus 10 times 0.3. And the result is the magic number minus 3 dB. So in conclusion, we found out that for the frequency response, which is practically represented in dB. We have this kind of plot here, which represents the low pass filter in dB. This one is 0 dB, and this one is FC or omega C. Let's do omega C to be coherent. Omega C, and this value here is equal to minus 3 dB. This is why you see that most of the time in the literature they say that the cutoff frequency is the point at minus 3 dB in the frequency response. Of course, you need to know where it comes from. Now you know it. At least I hope I proved to you where does it come from, and maybe you already have seen with Jorgen. That would be even great. So you just was just a review in that case. Okay, so then I will we can take a break and we can continue in 10 minutes. So again, when you calculate I mean, we found out now a lot of information about this plot. We found out how to represent this plot in dB. We found out that the maximum value is 1. We found out that the high frequency is 0. In dB, instead, is the maximum value is 0 dB. The minimum value is minus infinity, and so on. So we found out many information, but again, we still did not find the value or a formulas how to derive the cutoff frequency. I mean, this is nice. This is a practical method to look about the plot, search 1 over square root point, and then go to look about FC. If I have the plot, this is very nice, but we would like to have a formulas, right, to calculate the cutoff frequency. Again, you can still remember that the cutoff frequency is certain formulas, but again, it's always important that as engineer, you know where it's come from. Because again, the reason why I'm showing where it come from, all the things, is not because you have to remember it or because we have to fill some hours or whatever. But if you become engineers in this field, it happen many times that you will have to solve circuit that you never seen before. So you need to know the method. Once you know the method, then you can solve any circuit. If instead you remember now the cutoff frequency is now 1 over RC, whatever. But if I tell you what is the cutoff frequency of a 6-order filter, which is six capacitance in the circuit, you cannot tell me 1 over RC, 1 over 2 pi RC, because it's not true again. You have to solve the circuit and then find out what is the cutoff frequency of that filter. So not all the filters have the formulas already written in book, and most of the time you have to calculate on your own. So if you do not know the method, then you are like a technician. Just you say to the technician what to do, and then they do it. So I mean, I have so much respect for technician, but what we are aiming to here, I hope you are aiming to become is an engineer, which is someone that is not being told what you have to do, but you have to tell the other what to do. So, okay, but let me see, there is a comment. Yeah, you can write FC instead of omega C, is the same. In that case, I suggest you to write everything in terms of F. So in that case, I suggest to write everything like this: FC, F, and H of F. So everything is coherent to the fact that you use FC. Again, sometimes I also have I write omega C in the plot where I use the F axis. So it's not a big error, but try to be as much as coherent as possible with your plot, with your unit, and so on. That is kind of important when you write official documents and scientific publication or whatever. So I have to teach you how it should be done also kind of professionally. So try to be always coherent. Okay, so as I said before, it's very important to know where it comes from, the formulas of the cutoff frequency, and this is pretty trivial. Again, I show you the method, but then you can use the method for any kind of situation. So the point is that we have to practically use these formulas here, this one here. And so I'm going to rewrite that formulas there, here. So we have it here, H omega C. So the frequency response evaluated in omega C is equal to 1 over square root of 2. But for our circuit, which is the RC circuit, low pass filter, we know how much is this value, right? We know the formulas based on the impedance calculation we have done at the very beginning, which was 1 over square root of 1 plus omega square r square and c square. So we know that this term here has to be equal to square root over 2. Now what we do is we elevate everything to the power of the second power, right, to remove the ugly square root. And then we do 1 plus omega square r square c square equal 1 divided by 2. We rotate both fractions, right, because we are master of math, so we can do this. And then we bring the 1 on the other side, like this. And finally, remember that actually here I have to be precise, because remember that these formulas here is the frequency response at omega c. So it's important that here in the formulas I always put the c, because I remember that this omega is the omega c. It's not just a variable, but I'm focusing now is omega in omega c. And finally, we can find omega c square is equal 1 divided by r c square and square. And this means that the cutoff frequency of filter is equal 1 over RC. If you like to write it in terms of, because this is the unit of this is radiant over second, sometimes you don't like, and you want to maybe write in terms of frequency, so you have to divide for 2 pi, right? So the cutoff frequency here is 1 over 2 pi RC. And this one is measured in hertz. So, I mean, all the formulas that we write here is actually not magic. So this 1 over 2 pi over c is not that someone wake up and come out with these magic formulas. All of you should be able to calculate it. All of you have sufficient knowledge to do this. Okay, someone asked where come from the 1 is the value of r. I'm not sure where you are. Do you intend this r here, this one here? Which one? Which one you mean, Ole? Because I have more than one. So 1 plus omega c. Let me see where it is. You mean here? Okay, this just for the sake of maybe you got it, but I think maybe I got what you meant. Maybe you meant this one here. And here was just because, just for remembering everyone, that when you have a complex number, you have a plus jb, which is this is a complex number. And when you find the magnitude of the complex number, you do real part square plus imaginary part square, everything under the square. So in this case, you have a square plus b square, right? In our case, if you remember, my complex number was 1 plus 1 plus j omega rc. So the real part here was 1. So when I do this absolute value here, then we have the square root of 1 square, which is 1 plus omega square r square c square. Yeah, it was a good question. So we just review also these basic things if someone forgot, and it's always nice to review them. Okay, but for the sake of keep everything about electronic, then we remove it. Ta. Okay, someone of you already asked me also last time to put these notes in the canvas. I can put, but there is an ugly things in OneNote is that when I print, maybe I can show you so you are also seeing that, and maybe someone of you, what happened? Maybe someone of you will help in the lab to figure it out how to do it. I can print these things in PDF, but then for some reason, for some ugly reason, you see in the bottom of this page, the formulas are cut. So I think it's very ugly in this way. I hate this OneNote for this reason, because here when I write, I'm not able to figure it out where actually the page stop. So I'm not, maybe there is some setting. Before I have another version of OneNote where it was written actually to set the margin, but still the problem is the same. So I cannot understand where the page stop. So I think if I transform in PDF, this one will be very ugly. I can do it if you think it may be useful, although ugly. Um, Otherwise, I can try to share the OneNote things, but who does not have OneNote then cannot open it. Okay, someone suggests Notability. That's good suggestion. So that for this time probably won't be possible. But again, I always try to write all the equation that I write here in your slides, so you have all this step in the slide. Actually, the only thing you may not have is because I just remembered this morning is this part here. I forgot to write it in the slides. I just remember now that this one could have been something important to look into it. So maybe we'll add it then into the slide. But usually I put everything into the slide. But if you just want this file because you want to go through again all the calculation we have done in class, then I can try to create a PDF. Maybe later in the lab we can discuss more. Okay, but I think I show you everything about filter, at least how to extract the cutoff frequency, how to plot the filter. Of course, you can repeat this procedure for the other filters. I don't have time now to show it for all the filters, but and this probably will be one of the questions of the Obgave to prove, maybe to show how to calculate the cutoff frequency of RL filter. Usually what I do is ask for RL filters because they are not so famous and not so used as the RC. So you cannot find many equation in the internet. So I like to put that one in the Obgave, in the oblig. But again, in the end, you will find it. So I know that it's not difficult for you. But again, RL is a little not so common as RC. So usually I give that one in the oblig. And today I should be able to finish to write the question for the oblig. Okay, so again, you can repeat all of these steps that we have done. I've done today here. And another thing, I want to show you that actually the behavior of low pass filter can be extracted also by using the concept that I explained when we review the electric Cacarezza theory, which was the following. I told you that times that a capacitance C is represented with the impedance zeta C, which is 1 over j omega C. And just based it from these formulas, I can understand, I can have a good estimation about the behavior of C alone. And if the frequency in these formulas is very high, then what happens is that C behaves like a short circuit. I hope that you can understand why, because this value drop to zero practically if omega is very high. If omega is very low, then this impedance here behave like an open circuit. If anyone of you does not understand this concept, then let me know, because this is very, 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 very important. So remember that the impedance is the equivalent of resistance in AC. So if the resistance is very, very small, then it's behave like a short circuit. And instead, if the resistance is very, very high, behave like an open circuit. So no current can flow in that case. The same for the impedance. So if the impedance is very, very low, then it behave like a short circuit. If the impedance is very, very high, then it behave like an open circuit. Now I want to show you that actually this concept is very useful, and for us engineers is very important because it gives you an idea about how the circuit behave without doing any calculation. So if I consider, for example, this, not the high pass filter, let's use the low pass filter, which we like it and is our friends here. Okay. Okay. Let's use this concept that I just explained you here in this low pass filter that you know how does it behave, but maybe we can extract a few more information, right? So we apply here a signal here, and of course, again, when there is a signal, there is a current, right? Like this. Okay, so what does it happen when the frequency is very high? I say before, when the frequency is very high, you can actually substitute the capacitance with a short circuit, right? So this capacitance behave like a short circuit. So you understand in this case that the current that flow here is maximum and is flowing all through this short circuit here. And it's maximum because the impedance of zeta C now is practically zero. So the only things that limit the current here is the resistance R. Only R limit the current through the circuit. Furthermore, you understand that because this one behave like a short circuit, then the drop voltage here over the short circuit must be zero. Because as you remember, the voltage across the short circuit is zero. So immediately, without any calculation at all, I can tell you that at high frequency, this circuit here will have output voltage zero, okay? So there is no need of any calculation or whatever if you know how components behave. At low frequency, what happened? At low frequency, you have that this, I told you the capacitance behave practically. Low frequency, I mean it's very, very low, okay, approximately zero. So high frequency, I mean very, very high. Here I write approximately plus infinity, but of course this is not possible, and it means maybe gigahertz or 100 of megahertz, something like that. For low frequency, I mean maybe 1 hertz or something like that. Just to give you an idea about what kind of frequency I'm talking about. So again, for low frequency, let's say a few hertz or even millihertz, something very close to zero, okay? Something very close to zero. The capacitance behave as an open circuit based on what we wrote here. So you can understand immediately that if this one behave approximately as an open circuit, there cannot be any current here, right? If there is no any current here, there will not be any drop voltage here. So VR here is equal to zero. So the voltage at the output must be equal to the voltage at the input, okay? So at low frequency, V out must be equal to V in. And again, this one is the same things that I proved you before with the calculation, but now I did without. So try to know how try to treat this component as, try to know very well how they behave, and then you will be able to estimate or have an idea about the circuit will behave without any calculation. This is what engineers should do. See a circuit and see how it behaves without almost zero calculation. Of course, a few calculation is always necessary, but minimize it is always better, because the more calculation we do, the more error we can do, of course. The probability of error increase. Yes, so this is actually something very useful. I remove it because this is a trick. Actually, I could also keep it. Yeah, maybe it's better I keep it. So, but I removed the previous case, so maybe here then you won't understand. Maybe what I can do is just like this, so I can keep it. I remove this one here and put the capacitance here. Yeah. So yes, so let's try maybe to use this one on something that we don't know, all right? So, or at least we may not remember very well. Let's try, for example, to analyze this kind of circuit here. So try to use the trick that I just told you and try to understand if this one is a low pass filter or an high pass filter just by thinking about the trick that I just teach you. So again, the thing is very easy. We have to just try to evaluate this one for high frequency and also for low frequency. And then we have already an idea about what will be the behavior. So at very high frequency, what happened? At very high frequency, an inductance behave practically as a short circuit, and at very low frequency, sorry, it's the opposite. At a very high frequency, the impedance of the inductance become very high, so then this one become behave as an open circuit. And the very low frequency, the impedance of the inductance is very, very low, so it means that behave like as a short circuit. So let's consider the case, let's call it case A and case B. In the case A, you have that the inductance is an open circuit like this, so that cannot pass any current. If there is no current, the voltage VR is zero. If the voltage VR is zero, then it means V out is zero. So here V out is zero. But remember that when we characterize a filter, we are always interested in the frequency response, and which means in H omega, okay? This is the parameter that define the behavior of the filter. And how much is H omega? Well, H omega is equal V out divided by V in, but we just found out that V out is equal to zero, so H omega must be equal to zero. Then in the case B, you have omega is very low. Omega very low means the inductance or spool work as short circuit, and then I can draw like this, so the short circuit, and this means that if you can see the input voltage must be equal to the output voltage. They are in parallel, right? So in other words, here V out is equal V in, and how much is H omega? Remember again, H omega is the parameter, the key parameter. Well, H omega here is equal V out divided by V in, but V out is equal to V in, so V in divided by V in is equal to 1. So this one is equal to 1. So here immediately, just by this simple analysis, you can already immediately understand which kind of filter it is, because H is 0 at low frequency and H is 1 at high frequency. So it means that I'm expecting a filter that does like this. This is 1 and this is 0. This is the absolute value of H omega, and this is omega. And this is simply an high pass filter, okay? I minimize I don't have to solve all of the complex things, complex imaginary things to understand that this is an high pass filter if you know how to use this method, you understand? Of course, some of you can argue the fact that this is simple because we have that the function is actually is called monotonic, which means from mathematics is a mathematic term, which means that it's always increasing. It's not increasing and decreasing. So in that case, might be more complicated. But that's actually the main problem maybe of this method. This method can be used most of the time. So okay, someone says low pass filter. Oh yeah, sorry. Because I didn't read this part here, omega low and omega high. That's correct. I draw it in the opposite direction. So this is a low pass filter because again, H is equal 1 at low frequency and H is equal 0 at high frequency. Yeah, thank you very much. Yes, so and as I was saying, this method has one problem, and the problem is that if the function, for example, is doing like this, then of course it's a little tricky to visualize this kind of like this curve by using the method that I show you. So this method is kind of like quite useful when the circuit has one reactive component, and when when the circuit is relatively simple. So the problem here, as you can understand, I hope that you understood now that what happened when instead we have more complex frequency response, like this, and like this. I cannot use this method, right? Well, as I will show you then we need another tool to solve these things, to predict the frequency response. And that will come out with the Laplace transform. If you know the Laplace transform, then you can draw any frequency response that you want of any filter, whatever it is. and you can draw it quite precisely, relatively speaking. So that's why Laplace transform is very important in our case, and I think it's very important you understand the mathematics behind. So well, we will talk about it. And yes, so another thing that is very important. So in the slide, I also put some maybe examples that you can solve. We already solved this RL, and then you can also solve the other example that I put there. Another thing that you have to know is about one definition, which is called order of a filter. Maybe you have already heard about it. Order of filter. The order of filter is like, it determines like, how to say, let's say almost the quality of the filter, okay? It's not really the quality, but you can think about it in some way. And I will explain you soon why. Because the highest is the order of the filter, the more ideal is the frequency response of the filter. So it means like this. So let's consider frequency response of a low pass filter RC, for example, that we saw before. And then what we do, we also draw the other part like this. This is the ideal, and this is the real. Of course, you understand that the real one is a little different than the ideal, actually quite different, because we would like that after FC, nothing pass through. But this is not the case, because in the real part, you can see that in this part here, we have still some signal pass through. The signal that pass through have a small amplitude than the maximum, but still pass through, okay? So this is kind of like, sometimes we don't want this, especially when we do filtering for music or whatever, because we will still listen. We want, for example, listen only the bass, but we will listen still the high tones of the music. Usually we will look more in detail about this when I will present the Fourier series. I usually show how to use LTSpice to filter audio signals, and I will come in the lecture with one audio file. We will listen it together, and I will show you how to use LTSpice to filter it, and then listen how it is at the output of the filter. So, but I hope you can follow me now. So this real curve is not actually, is different than the ideal, and the part we don't like is actually this part here, because we let pass a little this signal in this range where we don't want. Okay. So often it happens that you want that the real filter behave more like an ideal filter. So you want that the curve here become a little steeper, right? The slope become bigger, right? Like this, something like that. And you can do that if you, of course, you make the circuit more complicated. And when you do that, you say that the order of the filter increase, okay? So here maybe it's a little quite small, this picture, but I can try to draw it a little better, like this, and like this. You can understand the green line is still a real filter, and also the black line are a real filter, but the green line is a much better filter than the one that are represented by the black lines, okay? Because it is more similar to the ideal filter, okay? So the difference between these three filters I draw is the order. So the green one has high order, okay? It's in high order filter. High order filter. So you understand that based on this definition, you would like to have higher order filter all the time, right? To have an ideal response of your filter. However, this comes in with one drawback, with one disadvantage, and is related to the definition of high order. The order of a filter, you can prove that is also equal to the number of reactive components in the circuit. reactive components in the circuit. And remember that reactive components are capacitance, inductance, capacitance and inductance. So you can understand what is the order of a filter by counting the number of reactive components. Let's do an exercise very fast. Let me read one. Someone asked if yes, if we change the resistance and the capacitance in the low pass filter, then it become an high pass filter. Yes, that's correct, Andreas. Okay, so then let's do an example in the for this order. So if I take our little friend's low pass filter, then here I can ask you what is the order of this filter, and what I have to do is just check how many capacitance or inductors are in the circuit. In this case, there is only one. This means that this is a first order filter. Okay. If I have this filter here, and I ask you what is the order of the filter, then you see there are two reactive components, and then you can say this is a second order filter. I have to add something, a detail that makes the difference in the definition to make it more precise and to let you not fall in tricks, which means is the number of effective reactive components. So here you have to add effective here, number of effective reactive components. Why do I write that? And I will show you now why. Let's consider another example, maybe like this. How much is the order of the filter? Here we have one capacitor, one inductors, and then we have second order. And then I want that you answer me in the chat about this question here. How much, what is the order of this filter here? Of the last one that I drew. So let's see if you understood. So what is the order of the filter here? Lilian say 1, Ole 2. I would like to have more answer. Vanessa 2. More. Lilian 2. The other one fell asleep, or maybe someone else. Anyone else? I see that someone else. I would like to have a little more feedback, so I know if all of you have understood the concepts or not. But anyway, let's proceed. Okay, let's say 3. The answer here is actually 2. And the reason why is because, and is also the reason why I add this effective here, is because actually these two inductance here, they behave like one. So they behave like an equivalent inductance, which is L1 plus L2. So the total effect, you always have to check if there are some inductance in series or some inductance in parallel, because those inductance can be placed together. The same for the capacitance. If the capacitance are in series or the capacitance are in parallel, they behave like one, okay? So this is why this was a tricky question where the result, the answer was actually 2, although there are 3 components. But this is also why I wrote here number of effective components, because effectively in the circuit here, there are 2, although physically you can put 3, okay? So here physically there are 3. So in your circuit, in your PCB or your breadboard, there will be 3 components, but actually they behave like 2, because the 2 inductor in parallel, they behave like 1 inductor, which is smaller, right? So this is can be a little tricky. And when we do Laplace, I will show you that knowing the order of the filter is very important, because it can tell you how much is the slope here. what is this color here? The slope of this curve is related to the order of the filter, as I said before. So the higher is the order, the more steeper is the slope, the better is the filter because it's closer to the ideal. In the same times, there are some specific value of this slope, and you will understand how much is this slope value only when I will explain the Laplace, in particular what is called the Bode plot. We will use mainly the Laplace to extract the Bode plot, which is another way to represent the frequency response. So it's very important that you are able to identify the order of a filter. I want to emphasize again, all the concept I'm explaining now, we will use it along the way. So if you reach the end and you don't know the second concept that I explained, probably you didn't understand most of the concept I explained along the course. So that's why in this course it's very important that you understand little by little all the step we do. If we put, someone say, if we put a resistance between these two like this, maybe they are still in parallel, but maybe you meant something else like in the other way. So if you put it maybe some resistance like this, maybe. In this case, instead is a third order filter because the two inductance cannot be joined together. So it behaves like two different inductors here. So yeah, in that case will be a third order. Let me see the comment here. So if I understood correctly here, the question is what will happen if we calculate the impedance of the two inductors and the capacitance. So here what happened is that this is actually a particular kind of circuit which is called LC circuit, which is, some people call it an oscillator, and this circuit is also called resonator because it resonates at a certain frequency. I did not go in detail, but I'm sure that you have done it in LELC. This one might require a little time because I definitely want to avoid this. It is a very long discussion if I want to talk about this circuit here, especially this RLC circuit here, which is very important. So I hope that you remember from LELC, but it is a long analysis because, but again, maybe it's interesting also to do this kind of exercise. So I can try maybe to do a little about it. So that's very good about the question. So maybe I can try to analyze a little just to show what's going on in this circuit here and refresh a little the idea, but I won't go in detail. I want to do the same analysis I did for the capacitance when I use the differential equation, because that is a second order differential equation, and you know second order differential equation have many solutions. In general, complex exponential, but in our case then is a sinusoidal signal solution that we are actually interested. But I want just maybe refresh one thing about this RLC, which because I like that all of you know this is a very important circuit. Just one thing, RLC also, just to give you some information, because we are talking about filter, RLC is very common as used as filter, is a passband filter. So it's kind of like those filters that I told you before, is kind of like has this kind of response here like this. There are many things to say about this filter. I can qualitatively give you some hint or give you some information because it's important. The value of the R is very important, as well the value of C and L. The value of C and L determine where is this kind of peak. This kind of peak is 1 over LC if we talk in terms of omega, and if you talk about in terms of frequency, then it's 1 over 2 pi LC, which is practically called resonant frequency and usually indicated with FR. So this is why it's very important to know these 2 points. So the bigger is L, the biggest is L and C, the smaller is the cutoff frequency, and as the smaller is the resonant frequency. But also this R is very important because this R determine the quality of this passband filter. Okay, so the biggest is the R, the more wide is this passband filter. So the less nice it is, the passband filter. Okay, because remember that the passband filter in theory, ideally, it should be kind of like this. So you want that the signal pass on in a precise frequency. So you understand that if you have some passband filter like this is a very ugly passband filter because you have all of the signal here and all of the signal here that pass through anyway. They are attenuated, yes, they are smaller, but they are still passing through. So you understand that the larger is this curve, the more uglier is your passband filter. So in theory, you would like to have a very, very steep here and then like this. This is a very good passband filter. And let's say the quality of this passband filter is determined by this value of R. So I can maybe show you like this. I did actually the previous year. I don't remember if in this lecture or another. Um, this is not a good representation. So let's do like this. Like this. Like this. And maybe like this. Okay, so from here to here, the value of R decrease. So the most wide curve has the biggest value of R. The thinner curve has the smallest value of R. Okay. So the smallest, let's say the smallest R is better. The smallest is the R, the better is the passband filter. I should actually prove all of these things, but it would take a little while to prove all of these things here, so I don't have actually time now, but I hope that at least this kind of like rule will help you to understand, to have an idea about what will be the plot. And in this case, talking about quality actually is also very important for engineer, that they define a quality parameter, which is called Q factor. The Q factor of a filter determines the quality of the passband filter, only for the passband filter. And for this circuit here, RLC, the Q factor can be written as omega L divided by R. Yes, so this is the Q factor, is one way to determine the Q factor, where omega is actually the resonant frequency, okay? So let me write it here, omega RL, okay? So it's not a generic omega, it's the omega at the resonance. So is this value here, there are also other way to write this formula, and yes, break after this. And there are other way to write this formula. Actually, I think I'm missing something here. Maybe it's omega square. Maybe omega. I don't remember, to be honest now. It's not very important. The important of this, I mean, of course you have to know it, but now it doesn't come out. I do not remember this because usually I derive it. But the important is that you see that the R is a denominator. So as I told you before, if R is big, the quality go down, because as I told you, if R is big, then the curve become wide. If R is small, then the quality of the filter go up. The Q factor is going up. I think this one is correct anyway. This formula is correct, and I can tell you why before to go to break. Remember that whenever you don't remember a formula, or yes, of course you have to derive it if you can. I can maybe show you how to derive it, but whenever you don't remember, the first things you have to do is always the unit check. So verify that all the units are correct. The Q factor is a number, is just a number that quantify the quality. So there is no dimension here, it's dimensionless. R is an impedance, or is a resistance, which is measured in ohm. And omega RL, if you remember, this one is nothing else than reactance of the inductance. And also this one is measured in ohm, right? So at the numerator I have ohm, at the denominator I have ohm. Ohm divided by ohm is dimensionless. And this makes sense because Q has to be dimensionless. If I would have put here square, then Q would not be dimensionless anymore. So this is a trick that I hope I try to teach every year, and unfortunately I see in the exam some students, they don't use it, and then they do a very big mistake. So this is a very, very important trick. If you don't remember the formulas, do the check unit every time. I suggest you every exercise, when you calculate your formulas, do all the times at the end the check unit. It will tell you immediately if you did some mistake during the procedure. Okay, we can take a break, and in 10 minutes we can continue. Just a little, start a little early, and so I can finish this filter, nice filter here to review a little. I think it's actually useful to know to use RLC because is an important circuit which you will find out in many situations. I didn't want to spend much time because I thought maybe Jorgen have explained quite in detail about these things, but because it's an extensive things, but I can still give you some, definitely my point of view of this device and maybe how this device can be used as a filter, probably so I will start maybe from that. Before I give you some brief overview about that, maybe I can give you a little more detail about this RLC circuit. This part, since I'm making it up now, then is not in the slide. I will maybe upload it in the slide later on. So, okay, but let's start very fast. I want to finish all the lecture for today. So with the amplifier and driver and so on. So I will try to be relatively fast here, but and slow at the same time. Okay, so how to build a filter with RLC. This is the typical schematic that you can use, for example. This is R, this is C, and this is L. Okay, so how much is the output voltage? Output voltage is equal to voltage divider. I won't repeat everything. J, yes, okay. Let's write it all so you understand. Zeta L plus zeta C, multiply for V in, of course, R divided by R plus J omega L plus J1 over omega C. And then I write R divided by R plus J in common omega L minus 1 over omega C. So this is yes, so zeta, yeah, so of course my L and C are very ugly, but here this is zeta L and this is zeta C. So here you can see that the output, thank you very much, Vin, and the output voltage depend on the value of omega mainly. The variable here is omega, and you understand that there is a particular situation in which this part here cancel each other. So what you can think about it is that is there any value of omega at which this difference becomes zero? That is the question. Does this one become zero for any value of omega? And that's the case. How to answer to this question? Well, we have to just set the equation as we just described in the question, right? So omega L minus 1 over omega C, we have to verify if this one can be equal 0 in some way, right? So we have to find the value of omega that bring this one to 0 and check if this is possible. If we solve this equation, then we get omega L equal 1 over omega C. Omega is equal to 1 divided by omega LC. Yes, and then since my unknown is omega, then omega square is equal 1 over LC. Therefore, omega is equal 1 over square root of LC. So there is a frequency which is called resonant frequency, which this is the formulas that how it come out, at which this imaginary part here is cancelled practically, right? And so what happens if that imaginary part is cancelled? Well, you saw before that if the imaginary cancels, so let's write like this. At omega equal omega r, what happened to the V out? It's very simple. You can see that if the omega L minus 1 over omega C becomes 0, then you have just R divided by R, which is 1. So V out become equal to V in. So when you are at the resonance, the input signal pass through to the output. Let's have a look about instead what happened for high frequency and low frequency. This is actually not a big deal if you remember our method that we applied before. At very low frequency, let's just do it. High frequency and low frequency. So then we have RLC. In the two situations. So at high frequency, we say that this one, the inductance is an open circuit, the capacitance is a short circuit. At low frequency, the inductance is a short circuit and the capacitance is an open circuit. So you can see that in both cases, current cannot flow because there is one of the two between capacitance and or inductance that is an open circuit, right? So if the current cannot flow, the voltage VR is equal 0, but voltage VR is equal V out. So the voltage at V out is equal 0. So at very high and very low frequency, you have that the frequency response is equal to 0. So we say that at omega R, we have that this one is 1, and then we know that for low frequency and high frequency is going to 0. So again, it makes sense to expect something like this in this case, right? And this is what happened actually. This is a passband filter. This is just an application of the method that I explained today. Okay, so I want to give you also a little insight about what happened actually. So we know that the voltage at the resonance is maximum. So it means that the resonance, the input voltage pass through, right? Pass through the filter and go to the output. And then I also talked before about the quality factor of filter, and I want to maybe give a little more information about it. Let's consider this circuit like this, which is the RLC, and let's consider an input voltage V, and here a switch. Okay, this is a switch. If I close the switch, if the switch is closed like this, so here the switch is closed, then what happens is that the current start to pass through. And then after a little time, I open the switch, okay? What is going to happen in this circuit? Well, you know that when a current passes through a capacitance, the capacitance charge, right? And let's actually, this one is not a good example, so let's do like this. Let's say that without the switch, otherwise it becomes too complicated. Let's say that, I repeat the example. So let's say that at the very beginning, the let's say T lower than 0, the voltage source is off. At T equals 0 become on, and then at T equal T1 become off again, okay? I mean this source here. So at the very beginning is off, then become on, then I turn it off again. So when I turn it on, right, start to flow some current, right? And then I turn it off again. What happened at this point? Well, you know that when the current was flowing, right, The capacitance is charging, and also the inductor is charging, okay? But then the power supply is off. But what happens is that the capacitance starts to discharge, but when it's discharged, when the capacitance discharge, it's practically charging the inductance on the other side. And so the capacitance discharge, but in the same time charge the inductance. Then the inductance discharge, and then the capacitance charge. So you understand that the energy in the capacitance and the inductance is stored in different moment of time. So if this one is time, if in this situation here, the energy inside of the capacitance, let's call it EC, is maximum, then the energy in the inductance should be minimum, because this means that the capacitance is fully charged, but the inductance is full discharge. When the inductance is fully charged, then the capacitance has to be fully discharged, and so on. Yes, so what happened actually when you turn off the switch, when you turn off the power supply, is that the inductance and the capacitance exchange the energy between each other, okay? The problem is that there is this ugly resistance here that is actually doing something very bad to the L and C, because you know that when you have current through it, then you have that the power is becoming heating. So you're practically dissipating the energy. You are consuming energy. So the problem here, what will happen is that it will not happen what I say before, but what happens is something like this. So the energy that the inductance and the capacitance exchange reduce in time, because little by little the energy is consumed by the resistance, okay, which become heat, okay. So again, this is why this R is very bad for the resonance circuit. If the resonance circuit work correctly, then this capacitance and inductor will exchange energy indefinitely, infinitely. So if this resistance was zero, in theory, this circuit oscillate even without the power supply, okay, even without the input signal, will continue to oscillate indefinitely. However, unfortunately, all the circuit, because the wire have a parasitic resistance, we already talked about it. So any circuit has parasitic resistance. So little by little, the energy that is exchanged by L and C is going to reduce. But I wanted to talk about this just because, to talk about the quality factor as I was starting. The quality factor, so you understand that the ideal situation is this one here, and the real situation is this one here. So the quality factor is defined as omega multiplied for the stored energy in the circuit at a certain time t, divided by the dissipated or consumed energy in the same circuit, of course, in the circuit RLC at the same moment, right? So how much is the stored energy? Here, actually, it's much easier to talk about power because as electronic, we like to talk about power rather than energy. But how much is the stored energy in the circuit? Well, you just need to look about the plot, maybe the ideal plot here, although in the real plot is the same, and actually look about this situation here. So in this point, for example, the energy of the inductance is maximum and the energy of the capacitance is minimum, is zero practically. So all the energy in the circuit is just stored in the inductance, okay? This is the L in the inductance, okay? So the energy in the circuit in this moment is just the energy in the inductance, which means the power in the circuit in this moment is the power in the inductance. And you remember maybe from ELEC that the power in inductance is 1/2 L E square. Of course, this kind of energy, so if I look in this point, is the same of this point. The sum of the energy should be the same, okay? The sum of the energy should be, the total sum of the energy should be the same. So it doesn't really matter if I evaluate here, here, or here. The sum of the energy should be the same. But it's much easier to calculate the total energy here because one is 0 and one is EL. So 0 plus EL is just EL. So the total energy is 1 over L divided by times E squared. How much is the dissipated energy? Well, you know from LL still, I hope, that the dissipated energy is just equal to 1 divided by 2 for, sorry, V times I, and then this one can be written also as I square R, right? This is the power of the in the resistance. So this one, wait, simplify this one with it. Okay, with this one and then this one. What happened here? This one with this one, and the result is the magic omega that I was showing before. So and why the what happened here? Why the definition of the Q factor is this one here? Because again, this dissipated energy is the part that we don't want because it's the part that creates this phenomenon here. So that is the part that dissipate, consume the stored energy in the circuit. So it's something we don't want. So this denominator here has to be as smaller as possible, right? The smaller is the dissipating part, the more ideal it is. It means that the capacitance and the inductor will exchange the energy continuously. So this is why the Q factor, which is the quality of the factor, is defined in this way. The higher is the quality of this RLC, the smaller is the dissipated energy. But again, you remember that the dissipated energy is related to the value of R, so which means that the quality factor is high as the R is small. Okay, so this one is just to show you where it comes from, the quality factor, and why it's like that. I think I did most of the things here. Yes. I don't think I want to show you anything else here. Of course, you have also the RLC in parallel, but is a similar story. I don't go there in detail, but I want that at least these things are clear, how to use the RLC circuit as a filter, and also what is one of the main what are the main parameters of this filter are omega R, which is 1 over square root of LC, and the Q factor. So the Q factor is also a very important parameter. Probably I will ask something about the Q factor in the oblique, so review this concept from LL. Okay, so I think I will go through the last part of this lecture today, which is about I finished to discuss about filters, at least give you an overview. There will be more to talk about it when I explain the Laplace transform, but for the moment, I think I give you an insight about the design of filters. Let's do also actually an example, just very fast, how to design a filter. We want to design a low pass filter which has cutoff frequency of 1 kilohertz. So that this is actually a very useful example because I show you how to determine values here, R and C. So the solution of this problem is very simple. We can use a very simple RC, right? But again, we could also use an LR. Then the question is, why should I use an RC rather than an LR? Any one of you know this? Both of these circuits are low pass filter, but why should I prefer one in respect to the other? I mean, at least based on my experience, I would prefer RC. But again, you can also prove the opposite if you think that that's something that you. So anyone has any guess? Which is these two is better and why, of course. One at a time. Okay, probably Jorgen did not go maybe into the detail of that. Well, someone say quality factor. The point is that the quality factor is something that I discussed just for the RLC. Again, maybe I wasn't clear enough, but the quality factor is something that is true only for the filter of RLC. passband filter, because the Q factor determines how the curve is wide or not, and we don't have any peak in the curve for the low pass filter and the high pass filter. Or in other way, I can also say this: we don't have Q factor in low pass filter RC and RL because we don't have any capacitor inductance that exchange energy, right? We have only one component, reactive component. So in this case, for RC and LR, we cannot talk about Q factor. So Q factor is only for passband. But thank you for the feedback. Anyone else can tell which of these two is better than the other and why? Is a very practical actually reason, and I can tell you then we should prefer RC because it's just for a practical reason, because to build an inductance, first of all, is a little more complicated than build a capacitance, because you need a copper wire and you have to roll it over a mechanical support in order that you create a coil, right? And if this coil is not built correctly, then it's difficult to control the value of the inductance. This is one reason, but also because since you have to create this coil, inductance are much bigger than capacitance. They take more space, and as electronic, we don't like big stuff because we are always trying to build a small circuit as possible. So this is why RC usually they are preferred. But LR, they are also used in particular application, which I'm not going through here. For example, in a laptop power supply, but for some other more advanced reason, and I'm not going to introduce it here. But the main reason why we have to prefer RC is because the dimensions are smaller. Okay, so then we want a frequency of 1 kilohertz, and we know that because now we are pro in this filter design, that the frequency for the formula for the cutoff frequency of this circuit is 1 over 2 pi RC. The question is, this one has to be 1 kilohertz. How do I choose R and C? Should I choose them randomly? Do I have any criteria? Well, when you design a circuit, the first criteria that you need to have, especially when you are in a student or a lab circuit, something like that, is which kind of component I have at home, which kind of component I have available, right? If you have your own lab or you have your own little components, your kit at home, whatever, before you have to check which component you have. This is the first criteria. But the second criteria then is this one. Usually capacitance are fabricated in smaller, there is less choice in choosing capacitance than resistance. You can find in the market many value of resistance, many value, but the value of the capacitance is much limited. So there are not any value. So if you want a capacitance of 11 nanofarad, I don't think you will find it. You have to join one of 10 nanofarad and 1 nanofarad together. So it's much more difficult to find a value of C. So the most reasonable thing that you can do is just choose, first of all, the value of C, of a value that you know that exists, okay? In this case, what could be the value of C? Well, here you can go for experience, but again, my technique here is a little based on experience. I can try to explain it. What I know is that this is a frequency, has to be in hertz, right? In kilohertz, in this case, 1 kilohertz. So it means that the denominator will have a unit around millisecond, because the opposite of a kilohertz is millisecond. And this means that the product between the resistance and the capacitance should be millisecond. So I can create milli by doing, for example, kilo and micro, because the product between kilo and micro is milli, okay? So I can think about something of capacitance of microfarad. Or in the same way, if you want to use some smaller capacitance, you can think about nano, but then here you need a mega ohm resistance to have milli, right? So this I know is a little intuitive, but when you become a little more experienced, you will also do like that. So in this case, if you understood my very maybe not so clear explanation, I will choose a capacitance of maybe 1 microfarad. And so I'm expecting that the resistance will be around maybe 1 kilo ohm or even less. The problem is that we have this 2 pi factor, which will reduce the value, not in kilo ohm, but maybe 100 of ohm. So yeah, 1 microfarad could be a good solution because 1 microfarad is easy to find in the market and so on. So, and then you're going to find the value of R. So FC divide, no, R is equal to 1 over 2 pi FC times C. Here again, let's try not to use, I also use 1 because it makes simple the calculation, okay? So let's try to not use the calculator if we can. Let's see if it's possible. 1 over divided by 2 pi times 1 kilohertz multiply for 1 microfarad, yes. Then we know that micro multiply for kilo is equal milli, as I say before. Then we have 1 divided by 2 millisecond. 1 over 1 millisecond is kilohertz, so it's 1 over 2 pi kilohertz, which means that is 1 over divided by 6.28, more or less. Let's say 1 divided by 6, and this is equal to, of course, kilohertz. 1 divided by 6 is 0 0.1, let me see. 10 divided by 4, 0.16 maybe, something like that. It's not really important to know the precise. Maybe someone of you can also verify with the calculator, but approximately should be 0.16. So it's not very important what is the value of the resistance again, because again, there is a tolerance of the resistance. So in the end, even if you find 0.16666, and even if you go to buy a resistance of 0.16666, okay, here, what was it? Maybe I did one mistake because the unit should be ohm. Let me see. Yeah, this one should be ohm. Ohm and ohm. Always check the unit ohm, and here we have kilo ohm. This is kilo ohm, so this means that the result is 160 ohm, approximately, okay? So as I was saying, it's not important that you calculate the precise value of the resistance, because anyway, then there are the tolerance, so it won't be equal the value that you buy. There will be maybe a little 10% more or 10% later smaller, so it's not a big deal. Yeah, so this is how to choose the components, and this is actually the first exercise that we have done about design, maybe numerically. I have to also emphasize another things that is very, 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 very important as the other things that I'm saying, but this is even more important because it's used in your exam. In this case, in this particular case, this is the calculated value, okay? And this calculated value comes from this first assumption here of the capacitance. However, all the values in your design always and forever and ever must be real value, okay? Cannot be something that we cannot find in the market. In particular, in this course, you must use a resistance or a capacitance which satisfy this standard here, which is called E24. So E24 is a standard, so the manufacturers, they build the resistance and capacitance with a certain values, which are classified as standard E24. There are also other standard E12, E6, E60, and whatever. In our course, we use E24. So you can Google in internet, you can write E24, and it will show, you can write E24 resistor, for example, and it will show a table where it show all the value of the capacitance resistance. Actually, I will do it now, so we can do it together. Let me see how to do these things. So don't leave values if you're not sure that are belong to the E24. This is 160 ohm. I don't think is in the E24, so this one would be wrong, okay? Would be not, although the calculation is okay, but I might remove maybe half point or maybe 1 point because it's not satisfying E24, which means that you cannot actually build it. let me see if I can open here maybe. Let's see. So then I share here my screen. I hope you can see my screen. And I now Google E24. I can write E24 resistor, for example, which is much easier. And then you can take whatever table here it is. I just opened the first website. Here it is. So here you can find the value. I hope you can see my mouse. You can find the value for E24. So this means that here there is no unit. So you have to be able to read it. So this means that you can find resistance of 1 ohm, 1.3 ohm, 1.8 ohm, 2.4 ohm, and so on. But you can also find resistor of 1 kilo, 1.3 kilo, 1.8 kilo, and so on. And you can find also resistance of 1 mega ohm, 1.3 mega ohm, 1.8 mega ohm, and so on. I hope you understood. You have to just look about E24. You can see that the resistance was that I calculated was 160. So here, as you can see, we have 1.6. So 1.6, it means that we can find the 160 ohm in the E24. So the 160 I calculated then is correct. We can keep it, okay? But if it was 165, for example, or I don't know, 31, then there is no 31 here in the table, so you cannot actually, you have to change it, okay? So in our case, I calculated 160. Here we have 1.6, which multiplied for 100 give me 160. This means that 160 is inside of the standard E24, okay? I will try to do another example maybe to show. Please have in your maybe computer this table so I can just share my screen in the pad rather than showing here the table, because the pad is maybe more useful. Okay, so share it here. I go back here. Okay, so in this case, the final result that I want to see, so whenever you do an exercise, the final result that I want to see is the following. 160 ohm, and this is 1 microfarad. You have to draw again the circuit just with the values. Sometimes I don't understand what you write in your calculation. The first things I go to check is this result here. If this one result is correct, then you already get a lot of points. Then I will go to check the result if actually maybe you have just copied or instead is coming from your procedure or not. So, but this one is very important. So at the end of any circuit that you solve, you need to put the circuit like this. Let's do very fast another exercise example. Let's say, for example, like this. Now, maybe the inductance I give you for the oblique. So let's do this one here. This is a high pass filter. And we want a cutoff frequency of, I don't know, maybe 10 kilohertz, not 10 kilohertz, no, because we used it before, maybe 20 kilohertz. Okay, so then you know that the cutoff frequency is still 1 over 2 pi RC. So this one has to be 20 kilohertz. This means that I may choose again, maybe let's try to change it, 100 nanofarad capacitance. And then if I use that, then we know that the resistance is equal 1 over the pi to Fc multiplied times C. Is 1 over 2 pi. Fc is 20 kilohertz. Multiply for C, which is 100 nano. Again, let's try not to use calculator. Nano multiplied for kilo is equal to micro. 1 divided by micro is mega. So this is mega, whatever will come out. And the reason here is 1 to pi times 20 times 100, which means here 2000. And then, yes, and then we can simplify even more. Here become, let's do like this, 1 over 4 times 1000. mega something. Of course, will be mega ohm because the resistance is in ohm. And so this one is 0. I think I forgot 1 pi, right? Pi. And this will be 0.25. 1 divided by 1000, we can put it here. This part here, we can put in the units, so they become kilo. 0.25 pi kilo ohm. And then become 0.25 divided by pi kilo ohm. So then it become, let me double check if my calculation are correct. So we have 20 kilo stem nano, that is micro, that is mega, okay. 102,000, 2000 times 4,000, okay. This is pi. Yes. And instead of pi, I consider 3. So 0 divided by 0.25 divided by 3 is around 0.08 approximately. So it means that this one will be 80 ohm. So now you go to your table and you check if there is 80 or 8. I don't see any 8. There is 8.2 and 7.5. So it means that I have to now change the value in 75 ohm or 82 ohm. Which do you think is the best? Well, the solution is 75 ohm, because if you use 75 ohm, the cutoff frequency is a little higher, and you avoid to get in more noise that you don't want actually. So if you increase the resistance, you will have that the cutoff frequency become lower, and so it means that you let pass more noise in your filter. So the best value here is 75. But it can depend also on your application. In this case, we can assume that we don't want the noise outside the filter, so 75 is the best solution. Okay, so that very fast finish the. Actually, I don't think I have time, but let's. I was talking too much here. Let me see. Okay. Let's go back to the slide very fast. I hope that I can do everything now. Okay, we arrived to the last part, which is Amplifier Adc and Drivers. I won't discuss about amplifier in detail, just do an introduction. So as I told you before, an electronic sensor generates a very small voltage and current, and we need to amplify it to make it larger. For this, we need an amplifier. So if the sensor generates a current and we want to create a bigger current, in this case, we called about current amplifier, right? This is very straightforward. If the signal generated by the sensor is voltage, and we want a bigger voltage, then we talk about voltage amplifier. This seems pretty easy. So the type of amplifier depends on the type of input and output, right? So, but again, there are other amplifiers which is not maybe so common as you think, or maybe it's not easy for you to think about them, is when you have an input voltage of the amplifier, but you want an output current, which is large. In this case, you talk about transconductance amplifier. When you have a current and you transform it in an high voltage, then you call about transresistance amplifier. Why it's called transconductance and transresistance is because the output divided by the input the unit is resistance in the case of a transresistance amplifier, while the output divided by the input of the amplifier of the transconductance amplifier is a conductance, which is 1 over ohm. We will look about more in detail about amplifiers later on. I want just to say a few things about the last part of an electronic system, control system. Again, you remember maybe that, let me draw it, that we have in here, that in a system we have the sensor, then we have the filter, then we have the amplifier, then we have another filter, and then we have matching range circuit, which we will study later on. Sorry if it's very ugly, but, and then you have the ADC, and there we have the display if you want to visualize the data, okay? This is the display. This is for an acquisition system. For a control system, what you have to do instead, the system is a little different we saw last time. We have here maybe a microcontroller or something that processes the data, and then you have to control something, like in the case of a thermostat, you have to control the heater of the thermostat, right? So the thermostat is controlled by an electrical signal, which is analog. So we have to go back in analog domain. So we need what is called a DAC, which is digital to analog converter. And then we have what is called an actuator. I call it actuator, which is the heater in the case of the thermostat, okay? And that's all. So you cannot connect actually the duct directly to the actuator, because the actuator usually need a lot of current, a lot of power, like the heater to work need a lot of power. So between the duct and the actuator, usually you put another device, another circuit, which is called driver. Okay, drivers are very common in motors and other power devices. We will maybe look into it a little, but maybe we don't have time to look into much. But there are a few concepts about drivers that are very important. That's why I'm mentioning now. So whenever you connect to an actuator, which can be a motor, can be a heater, can be a speaker, then you need always a driver. Okay. And you need also a DAC in this case, because you have to convert the digital signal that you process into an electrical signal to control the heater, the speaker, or whatever. Yes, so the main purpose of this driver, so of course the purpose of the DAC is pretty understandable and reasonable, is transform digital signal in analog, so I don't spend times there. But maybe you may wonder a little about this driver. What is the purpose of the driver? The purpose of the driver is to transmit the maximum power to the load, to the actuator, okay, to the heater or to the speaker or whatever. So this is the purpose of the driver: maximize the power transmitted. Okay. In the case of the speaker, the more power you have, the more sound you have, right? So it's very straightforward. Probably I will finish next time about discussing driver, doing some calculation, but I want just to introduce a few things. This is a simple example where you have the loudspeaker that you have at home. Usually the loudspeaker is modeled as a resistor of 8 ohm. As I show you also the incandescent lamp or filament lamp, right? We also model it as a resistance. Also the speaker can be modeled as a resistance. So from electrical point of view, we can just replace it with the 8 ohm resistance. And you understand this resistance is very, very low. So we expect that here, if you apply, let's say 8 volt, here there is already 1 ampere, which is a lot. So the circuit should be enough strong, should be very robust to deliver this 1 ampere. So in this case, we need a driver, which most of the time, another way to call the driver is a power amplifier, okay? So we need to connect a power amplifier to give the energy to the loudspeaker in order that the loudspeaker create a very loud sound. How do we model this one from electrical point of view? Again, this is a real situation. As I told you, the loudspeaker can be modeled as a resistance. And how do I model the power amplifier? I told you that the power amplifier is something that generates a signal, so it's an active device. And we saw before from last lecture that all the active circuit can be modeled with a Thevenin equivalent model. So I can just replace the power amplifier with an equivalent model, and now it's very easy to understand actually how to solve this circuit, right? The problem is, in your case and also in many situations, you are going to design this power amplifier. And this power amplifier will have a signal, which is this VTH generated, but also the main thing you have to design of the power amplifier is the output resistance, which is practically here modeled by the Thevenin's resistance here. So the question is, how much should be this resistance here of your power amplifier? How much should be the output resistance of the power amplifier? Well, I will maybe show you next time with more calculation through it. I can just show you that I already have prepared it here. I can show you the method. Maybe next time I will ask you if I have to go through the calculation or not, but I can show you it here. So my purpose is to find the condition which allow me the maximum power on the here, which is the speaker. In this case, I call it RL because L means load. which means is the load connected to the circuit. How much is the power here? You know that the power is calculated by using V squared divided by RL, and VRL is the voltage, sorry, VRL squared divided by RL. VRL is the voltage here over the resistance. The voltage here over the resistance can be found by using voltage divider or Spelling-Deller. And after that, you can find the formulas for the power. But then, what is the condition that give me the maximum power? Okay, what is the value of RTH that give me the maximum power, right? In the other, you can rotate this question, right, and say what is the RL value that give me the best power at the output. So yeah, so here there is maybe a little more to discuss about it. So let's maybe end it here. So conclude it here. So given these formulas here, the next step will be how to find the condition to maximize these formulas here, because we want a maximum power on the speaker, on the load, right? And so next time we will discuss more about how to solve this problem. This design problem is very common and will be use this concept many times. So the concept I will explain here in the driving part is very important. So next time we have to look into this. So I think for today anyway, maybe I don't want to go more through, because otherwise I need another 15 minutes probably to show what I want to show, and this one is very important, so I want to dedicate a little more time. If you have any question, feel free to ask now, because I know there are many things that's going on. And today I will, in the afternoon or in the evening, I will finish to prepare the preparation for the Oblique 2. So soon will be also ready the preparation of Oblique 2, and I will try to solve some exercise similar to the preparation of the Oblique 2, so you have it in Canvas. Remember that again, I want to emphasize, I like this because every year students say that there is a lot of things to do, but I think also that you have to learn how to manage your time very well. Start as early as possible to prepare to your oblique, and when will be the time to do the project. When I will tell you start to work on the project, you have to start to work on the project. If you wait, you will have a lot of things to do it later on, and then of course you will come to me and complain there is a lot of things. But I admit, and I'm aware that this course has many things to study, but in the same times you need also to manage very well your time. I know you also have another course, but personally, this is something that is my opinion and so on. This course is very important for you because you become electronic engineer or micro system, and you don't become an engineer in math, right? Math is important, definitely, because we are using it here, but give the correct importance to the different things you're studying in your career, I think. I'm not saying now that you have to neglect math, but try to balance very well the way that you give to the different things that you learn. Okay, said that, then I think I will turn off my computer and I will start to go toward the lab. Go in the lab in orderly fashion manner, like good student.